A new chapter, chapter 10, which is about infinite series. This right here is an example of a very famous infinite series, a power series. We will certainly, by the end of this chapter, you will be very familiar with this. But before we talk about series, the lead-in is going to be talking about sequences. So here's an example of a sequence. It's a very famous sequence, the Fibonacci sequence. It's basically a list of numbers. So we'll talk about the Fibonacci sequence later on. Another famous sequence, or quite reasonable sequence, is what would happen if you had a pizza and you started off with the entire pizza. So you have one pizza, and then you eat half of it. So now you have half a pizza left. And then you eat half of what's left. So you have a quarter of what's left, and an eighth, and a 16th, and a 32nd. And so we can keep doing this over and over and over to form the sequence of numbers, and numbers written out in a list. We can also start thinking about, well, these numbers are getting closer and closer and closer to zero. That kind of sounds like a limit from Calculus 1, and so certainly later on in this section we're going to be talking about the limit of a sequence. Let's go ahead and have a definition here. So here's a more formal definition of a sequence. A sequence A sub n, so the terms here A sub n, we usually put them inside little squiggly braces to represent the fact that we're thinking of the entire collection of these terms, is an ordered collection of terms is a word for numbers here, defined by a function f on a set of sequential integers. So whenever we talk about n here, that n is the index here. More informally, when we think of a sequence, we're just thinking of a list of numbers here. And usually, almost always, our sequences are going to be infinite. So there will always be infinitely many terms in here. We usually start our sequences at a sub 1, or indexing starting with 1. Sometimes we index starting with 0. Sometimes we index starting with 2, or anything else. But all of this, these are all sequences. Here are two perfectly good sequences to think about. Okay. Oftentimes, a sub n is given by a formula. And so when a sub n is given by the formula, we can call a sub n the general term. Also, another definition here is the domain is going to be the allowable set of values of n here. So that would be, in this case, the domain would be positive integers. Going back to the general term here, a sub n being given by a formula. So in this case, well, let's say that we are calling this a1, a2, a3, a4, a5, a6, and we keep going here. So it looks like we're raising 1/2 to different powers here. So 1 is 1/2 to the 0. 1/2 is 1/2 to the first power. 1/4 is 1/2 squared. 1/8 is 1/8 is 1/2 cubed. So note what's the correspondence here. We're raising this to the third power for where the index is 4. We're raising this to the second power where the index is 3. We're raising this to the first power where the index here is 2. So it sure looks like here, and in fact it is the case, that a sub n here is 1/2 to the n minus 1. So that is how we can write our terms, write down the general term of our sequence. But we should be clear here. We should be clear that not all sequences, we don't have to have a formula in order to have a sequence. Sometimes we can just describe it in other ways. So for example, here's a sequence. Let me write down the first several terms of this. 3, 1, 4, 1, 5, 9, 2, 6, ... What's going on here? I'm just listing out decimal digits of pi. 3.14159, so on and so forth here. So the nth term is the nth digit of pi. And so this is a perfectly good sequence. We don't have a formula for it, and there's not really any reasonable formula, anything that you would like in terms of having a formula for the nth digit of pi. But we can just define a sequence in this ways, and that is a perfectly acceptable ways to do things. So think about this.